Spark, one of the great RISC CPU architectures. If you know anything about Spark, the thing you probably know is that it was used by Sun machines. But what if I was to tell you that Spark processors are not just all about Sun machines? Well, several of you will have just screamed liar at your screen and will already be typing something in the comment section that starts with the phrase, well actually. But for those who want more, tune in to after our small commercial break. Today's video is sponsored by PCBWay, purveyor of printed circuit boards. Yes, that's what PCB really stands for. They also do CNC machining, 3D printing, that sort of thing. And also injection molding. If you want to check out a nice example of their work, go have a look at Mark Fix's stuff, as they've made him a really nice Amiga case. I won't tell you any more, but yeah, do have a look. And as they say, link in the description below. Right, back to our scheduled programs. Okay, we are gonna have to talk about Sun, as the Spark processor very much does start with them, even though Sun is very much not the whole story of Spark. But I just want to get out there from the outset, this video is not the history of Sun. Firstly, because I really want to talk about Spark, and Spark is more than just Sun, and if you just talked about Sun and its history, yeah, you kind of bury the whole Spark thing a bit. But also, I really want to do a video on the history of Sun, and I don't want to cannibalize that video for this one, if you see what I mean. So it's okay, for the more angry Sun fans out there, you can put your pitchforks down. Your time will come. Yes, I'm talking about you there with the beard. And now, with all that said, let's talk about Sun. Sun's early years had gone pretty well. They built themselves a number of workstations, built around the Motorola 68000 and its follow-up processors. I mean, Sun weren't the only people building systems around the 68000. In fact, most of the Unix workstation market seemed to be based around that thing at one point. Apollo's domain workstations, they were based around the 68000. Even early SGI kit, based around the 68000. Torch's Unicorn, 68000. You name it, Unix vendors from big to small, 68000. But the times, they were a-changing. And the thing that was helped driving those times that were a-changing was a research project at Berkeley that was looking into RISC, Reduced Instruction Set Computing. Now, I'm going to go on a little tangent here for a second just on the history of RISC, because every time I mention one of these CPUs and that, well, they got their inspiration from the Berkeley RISC project, someone always posts in the comments, but IBM invented RISC, and to those who posted that, yes, you're right, sort of. Yep, this is why we need the sidebar. IBM did create the world's first RISC processor, because internally IBM had come to the realization that all the code they deployed on their 360 mainframes used basically a small subset of the instructions available in their CPU. Who knew no one wanted to use the halt and catch fire instruction? So there was the realization inside IBM that they could make a chip with a lot less instructions in it. And there's a huge advantage to that when you're the people who are, manufacturing the processor. But IBM were not the only people to come to this realization. In a well-known paper published in 1978, well known by people who quite like CPUs, Andrew Tannenbaum, who'd later become of Minix fame, demonstrated the same thing. He took an example of a 10,000 line program and showed that it could be run with a much smaller instruction set. Now this went on to inspire two research projects, the Berkeley RISC project, which Sun very much borrowed for, and also the MIPS project at Stanford. The RISC project at Berkeley was headed up by David Patterson, the man who'd also coined the term RISC. Now this particular project became quite well known because it published a number of papers. Also, so did the Stanford one, but we'll cycle back to that in a second. And it's these papers that inspired various other RISC designs, because these papers were available. You could read them, you could look at them, you knew about them. Whereas IBM's work in RISC, you didn't know about it, they didn't release that many papers and no one really saw them. So when I say that these processors are inspired by the Berkeley RISC project, it's because they literally were. IBM's RISC chip may have come earlier, but also it's hard to be inspired by a thing you don't know about that IBM doesn't particularly talk about either. The other reason we know that Spark was inspired by the Berkeley project is because the people who designed the chip told us it was. And you can see why. Lots of research papers, it demonstrates how fast it is, and also Berkeley's first two chips, the RISC-1 and the RISC-2, were implemented by students in a class. If you're a workstation vendor who's still relatively small, let's face it, as Sun was then, knowing that one of these processors could be designed by a bunch of students kind of makes you think, well, maybe we could do that. I mean, that's the sort of resourcing level we've got, right? As a brief sidebar to the sidebar, We also know ARM was very much inspired by the Berkeley project because Sophie Wilson told us when she was first thinking about the instruction set for ARM, she did so because she'd read a paper about the Berkeley project that she'd been given by Andy Hopper. And again, knowing that work had been carried out by a small group of students, and also discovering that a bunch of students were currently designing the processor that the Western Design Center was creating to replace the 6502, also made them think, well, maybe we could do that too. Knowing that the world's largest computer company has happened to create a microprocessor does not make you think, well, if they can do it, surely we can too. But knowing a university group has, well, that's a whole different kettle of fish. Now, I did mention before the Stanford project and said we'd cycle back to it, and here we are, this is the moment where we're cycling back. Stanford's MIPS project was actually pretty inspirational as well to lots of different designs, again, because it had a lot of papers out there where people could see what they did and learn about it. It's also a viable scale for a lot of these companies. Knowing that IBM's done something, for example, makes you think, well, maybe we can't do that because your R&D budget is not that dissimilar in cash terms to IBM's catering budget. Although IBM's catering did play a small role in the downfall of the Soviet Empire. If you don't believe me, look up Khrushchev's visit to an IBM factory. Yeah, he discovered some pretty harsh realities on that day. Although, switching back to discussing about SPARC again, and reversing back up a few sidebars, we can tell the SPARC design's much more inspired by the Berkeley design because it uses something called register windows. I'll explain what those are in a minute, but that's the big difference between Stanford's MIPS project and the Berkeley one, in that register windows were a Berkeley thing and not a Stanford thing. It's worth noting that Silicon Graphics SGI, one of Sun's big competitors, it went very much down the Stanford route as it literally purchased the MIPS technology. As we've mentioned registers a few times, it's time to discuss them and what makes a RISC processor a bit different to a CISC processor. Now, you probably already guessed by the name Reduced Instruction Set that a RISC processor has less instructions, or something I directly said earlier that it did. But it is worth saying that there's more to the difference in complexity than just the number of instructions themselves. Now, admittedly, some CISC architectures like VAX, for example, had an instruction for almost everything. But coupled with its 18 million instructions, it also had various different ways of instructions accessing data. In CPUs, you have these things called registers, which is a small bit of memory that lives inside the processor. Sometimes these registers have special purposes, like the instruction pointer that points to where the CPU is running its next instruction from in memory, or the stack pointer that tells you where the stack is. But you also have general purpose registers that the developer can use. So on the original processor used in the PC, you've got 4, A, B, C, and D. Say you wanted to add two numbers, well, you could run the add instruction and tell it that it wants to add register A to B and put the answer in C, for example. But in CISC processors, it's not that simple. You don't just use registers. The same add instruction could be given a memory location and a register and told to put the result back in another memory location, or it could be back into a register. Or in some cases, the location in memory could actually be a pointer to another location in memory. Or for good measure, you could just whack a constant in there like 2 as well. So in CISC processors, not only did you have all the complexity of all these extra instructions, all these instructions were complicated by the ton of different ways that you could hand the processor the data that it was going to operate on, or the operators. Now the Berkeley design did away with that, and SPARC copied the same thing, and it became what's known as a load store architecture. So if you wanted to add two numbers together and write them into a particular memory location, well, you couldn't just bung that on the instruction for add. What you had to do was issue a load instruction that would load a value from memory into one of the registers. You would then load the next value again from memory into a register. We've used 2 instructions. Then you would do add, and add would deposit the result in one of the registers. And finally, we'd then run our 4th instruction that would store the value back in memory. Now you'll notice this is 4 instructions versus 1, and you might be thinking, well, that sounds slower, doesn't it? But RISC processors, even from the earliest Berkeley one, had a sort of pipeline type idea. So while it's running one block of code ahead, it's running those load from memory instructions, so when it gets round to running add, the data's already in the registers ready to go. Now, ditching all these addressing modes, and there are still quite a few I didn't mention in the examples earlier when we didn't do memory location plus 2, for example, well, it greatly reduces the complexity of the chip, and by reducing the complexity of all the circuitry, it means you can crank the clock speed up, and this thing can go pretty fast. I mean, if I give you an example of Berkeley's second RISC processor, ran somewhere between 120 to 240% faster than the Motorola 68000 at the same clock speeds. You can understand for a workstation vendor that's currently on 68,000 that this whole RISC thing may be super attractive. Now you can see from the example I gave earlier that the use of registers is really important in RISC design. And during the phase where we have two universities both working on their approach to risk, we end up with two ways of trying to optimize the use of registers. MIPS' approach at Stanford reasoned that the issue was not the number of registers but how efficiently they were used. So they went with, let's make the compiler optimize the use of registers. Whereas Berkeley, and also followed by Spark, decided to use a concept called register windows. Now in the Berkeley chip, for example, this meant that internally the CPU had 64 registers, only 8 of which could be used by code at once, and the window would change which 8 can be used at a time. Now Spark borrowed this idea but changed it a bit. In the Spark architecture, you have 4 groups of 8 registers, 3 of which are windowed, and they all have a purpose. So the first group of windowed registers I'm going to talk about are numbered I0 through to 7, and these are intended for input when you call a function, so you put your function call values in those registers. You then have the next set of windowed registers, which are L0 through to 7 again, 8 registers that you use as local registers inside the function that's being called. The final set of windowed registers are O0 through to 7, and they're used for the output of the function. And finally, you'll note that we have 8 registers left that are not windowed at all. These are fixed and point to the same set of hardware registers every time, and these are registers G0 to G7, and they're used for your global variables, hence G. Now, using register windows is one of the big architectural decisions for Spark, and also pretty strongly marks out that it comes from the Berkeley tradition and not the Stanford MIPS tradition. Although Spark is no slouch in the performance department, there does seem to be a few papers suggesting that the MIPS approach to doing this of optimized the compiler in the end did work out a little bit more performant. Although, I should mention, Spark is not the last architecture to take this approach. In fact, Intel's ultimately doomed Itanium processor would also use register windows, only the number of registers available in each window was variable. Although I should mention, there's some irony here in Itanium choosing this one bit that doesn't need to be optimized by the compiler, when the whole rest of the chip required the compiler to basically be sentient in order to run at a decent speed. Spark was first developed in 1986 and finally shipped in 1987. Yes, we got what was going to be known as version 7 of the architecture. Goodness only knows what happened to versions 1 through to 6. I guess they were just internal. You'll see a number of articles and videos refer to Spark as the first commercial RISC processor, which is of course true if you ignore all the other commercial RISC processors that came before it. I think what those articles and videos are trying to get at is that Spark began the trade in the Unix workstation space of having small powerful RISC processors at the heart of the system, as most vendors before that were using 68,000 base machines just like Sun. Well, as soon as Sun was out there with their Spark-based systems, everyone else felt that they had to jump on the bandwagon too, and boy and how did they. HP developed their own RISC processor, DEC finally stopped messing around with Prism and started work on Alpha, Motorola decided it wanted to stay in the processor market and develop PowerPC. And of course SGI started first using MIPS and then bought MIPS Technologies. And Spark was the starting pistol for that whole race. But of course, Sun were fairly clever. Sun realised they didn't want to be the only people making the Spark processor. This is not the first time that Sun embraced an open standard. Before this, Sun had released its NFS as a standard that other people could implement. And in fact, it's a standard that has completely managed to outlast Sun itself, as you'll find NFS supporting basically every operating system that's still in commercial development, and almost every single NAS out there has NFS support. Heck, even my TV supports NFS. Although that said, I really don't think that's a particularly common TV standard. Sun have, of course, in the past also abandoned its own proprietary standards to adopt an open one. A good example of that would be with X Windows. Originally, Sun had their own GUI system known as News. But when the rest of the world decided that they'd get together and try and work on something and created X, well, Sun jumped on board. What Sun had figured out is that a lot of the time it is better to be one of the leading providers of an open technology than it is to be the only provider of a proprietary technology. With a proprietary technology, you have to do everything that lives around it as well as the core product itself. With an open technology, well, lots of different companies can get involved and make that whole ecosystem, well, a lot more vibrant than it otherwise would be. And this helped create a larger market for Sun to sell into. Let's have a look at the first CPU produced as part of this opening up of Spark. And that's the MB86900. Catchy little title, isn't it? Produced by Fujitsu. Now this chip was entirely designed by Sun, but Fujitsu were the silicon partner, so actually did the manufacturing of the chips. As Sun didn't actually have any chip fabs of its own, or in fact a team to do, well, any of the work involved around that. Now, this was the SPARC processor that Sun would use in its first line of SPARC-based workstations. Fujitsu at some point would also make its own series of Sun clone workstations. And over the next few years, Sun would design another version of the chip that they would get lots of different people to manufacture. Of course, Fujitsu would not stop here. In fact, they would go on to design a lot more SPARC-based processors when we move on to version 8 of the architecture. Now, how version 8 gets defined is a whole different kettle of fish to how Sun just did version 7 by themselves. Now we have a body known as the SPARC Architecture Committee that has quite a few different companies on it, one of course being Sun and Fujitsu. We also see a few other big names pop up on that list like ICL, LSI Logic, Matsushita, Philips, and we also have TI, some of which have been involved in manufacturing SPARC processors for Sun. We also have some new small companies turn up who are there to get into this new SPARC space. The main name here being Ross Technologies, who we'll talk about in a moment or two. The other company I've not mentioned yet is Amdahl, a company you may not be that familiar with, but it was founded by one of the people who helped design the IBM 360 mainframe, and would go on to be purchased by Fujitsu. Now, version 8 doesn't change things too radically. We get a couple of instructions added. We'll get an actual integer multiply and divide. That's actually pretty important. We also get an upgrade to the floating point that moves from 80-bit to 128-bit. Ooh. In fact, this version of the SPARC architecture would actually become an IEEE standard. This is also where we see a bit of an explosion into the various models of SPARC processor that are available from different suppliers. And with this variety of companies being involved, we also see chips getting designed with a variety of markets in mind. Some were aiming at just the big Unix workstation end of the model, whereas others, like Fujitsu, TI and LSI, they're wanting to produce much smaller SPARC processors targeted at the more embedded end of the market. So in that regard, we start to see the MicroSpark and the Spark Lite from Fujitsu. In fact, we even get to see a second version of the MicroSpark. But that doesn't mean that Sun are just left to do the high end. For example, Fujitsu developed the TurboSpark. And of course, a new company, Ross Technologies, is formed to produce high-end chips. In fact, Ross Technologies is the one we're going to have a deeper look at, by and large, because I find them the most interesting of the lot, and also, I've got a machine that's got a few of their HyperSparks in. Ross Technology was founded by Dr. Roger D. Ross. That's a name that will be familiar to some of you, well, assuming that some of you are people who are a bit nerdy like me and like CPU architectures, as Ross headed Motorola's Advanced Processor Division, and was responsible for overseeing the design of the 68030, and also their RISC chip as well that was a bit less successful. Now, of course, when he started Ross, he was not the only Motorola employee that left to go be part of it. So did Carl Dobbs, Janet Scooch, Steve Goldstein, and Trevor Smith, all of whom were also members of Motorola's Advanced Processor team. And of course, Motorola being Motorola, they took this extremely well. No, they tried to sue them. That does seem to be a bit of a habit for Motorola. Leading processor designer leaves, Motorola sues them in their new company. See the Chuck Peddle video for details of other instances. A lot of the other companies involved in making SPARC processors had either done so in conjunction with Sun, say like Sun and TI both worked on the SuperSpark together, or Fujitsu, or they'd only targeted the embedded sort of low end of the processor market. But Ross was going to make a high-end SPARC processor. Now, Ross Technology didn't just come out of nowhere. They were in fact predominantly funded by Cypress Semiconductor, who for years had been making all sorts of varieties of chips, but no high-end processor. So this can be seen as part of Cypress's desire to become one of the top-tier chip producers. And in 1993, they released the HyperSpark, a SPARC version 8 architecture chip that was considered by most at the time the bee's knees. And if you're not familiar with that expression, the bee's knees means that it was quite good. I don't know if the knees of bees are actually particularly great as knees go, though. And what you're looking at in front of you now is the SPARC Station 10 with four whole HyperSpark processors in it. At the time, this would have been a particularly expensive workstation for a start. It's a SPARC Station 10, they were not cheap. But then, there's the 4 HyperSpark processors, that would have really pushed the cost up. Also, this thing's got 128 meg of RAM, which, at a point in time where 4 meg of RAM was considered good for a PC, yeah, this would have cost all the money. Now, as someone who's been playing with this machine for a while, I can tell you, the HyperSpark's reputation is pretty well deserved. Long-term viewers of this channel may in fact recognise this SPARC Station 10 because it's the same one I used in my video on the Mac application environment, which was a system for emulating Mac applications written for 68,000 machines on a Unix system. And given all the emulation of the 68000 chip is done in software, this HyperSpark chip manages to emulate the 68000 faster than any 68000 I've ever had inside a Mac. And this is on a processor that came out before Apple moved to the running PowerPC in their Macs. So this is a contemporary to the 68000 and it emulates the 68000 series processors faster than the actual processors go. Now, one of the reasons this is so quick is it's got a number of architectural features we would see appear in a lot of processors as time goes on. In that it's a two-way superscalar design, it has 4 execution units, an integer unit, a floating point unit, one for doing the load and store, and a branch unit. There's also an 8KB instruction cache, which again doesn't sound huge, but actually for the time, really not that bad. There's also quite a lot of registers as well in that windowing system we talked about earlier. From that cache, every single clock tick, 2 instructions would be taken and decoded. The chip also had a pretty good instruction latency as well, and that latency would vary between 18 to 37 cycles. The chip, as you know, also had support for multiprocessing as well, and used something called M-Bus to allow processors to talk to each other, which was a Sun creation. Fujitsu was the main silicon partner for fabricating these things, although later versions were done by NEC. The problem for ROS, though, is despite all the technical advantages of the HyperSpark, it's still a difficult sell. What you're essentially trying to sell is a very expensive processor to get added into a very expensive workstation made by your competitor, who will also sell you a processor with that machine. Now, ROS did try and solve this, and by 1996 they were creating ROS Microcomputer, a company designed to create workstations and also server products. And they weren't the only company apart from Sun starting to make Spark-based machines. I'll come on to a few different ones in a little bit. What really did for ROS, though, was something that Sun did. Sun released the UltraSpark, a 64-bit version of the Spark processor, which left ROS's 32-bit version, despite the fact it was a very rapid 32-bit version, looking a bit dated and slow in comparison. Now, eventually all the bits of ROS that really mattered ended up being owned by Fujitsu, and in fact some of that ROS technology stuff would go on to become part of all future generations of the UltraSpark. Now, I said I'd mention some of the non-Sun-based Spark machines out there, so now is that time. Now, it's worth noting that none of these systems really got any large market share, although some of them were commercially very worthwhile, and we'll come on to the much more worthwhile ones towards the end. So, for example, Amdahl, the mainframe company, they ended up building some machines based around Spark. Now, these are not the sort of things you'd have in your house, or in fact in a medium-sized company, but if you have a really big data hall and a surprisingly large quantity of electricity, your business may have used one of these things. Another example of a Spark-based computer vendor who made machines that were more suited for people who didn't own their own power station was Solborn Computer. They produced mostly multiprocessor servers. In fact, they were doing symmetric multiprocessing before Sun was. In fact, Sun was only doing asymmetric multiprocessing at that point. But their stuff was fairly tied into Sun stuff as well because, well, they used a version of Sun OS for their machines, and also a lot of the market did think Spark meant Sun. However, they were a successful niche within the niche that was Spark. Now, the biggest manufacturer to produce machines around the Spark design, who were not Sun, was Fujitsu. In fact, unlike Sun, Fujitsu was still making UltraSpark-based machines. In fact, they have a whole new line of mainframes due to come out. Now, Fujitsu got involved from the earliest days of Spark because they were looking for a new processor for their range of mainframe machines. It'd be fair to say I'm not super familiar with Fujitsu's line of mainframes, as I'm not Japanese. As Fujitsu did not have a lot of success with their mainframe range outside of Japan, but in Japan, they had a lot of success. Now, part of this is because in the early mainframe years, dealing with the Japanese character set was a non-trivial problem for a machine. And Fujitsu got that cracked, whereas other Western suppliers, they didn't in any way, shape or form. Now, in the PC market in Japan, when more Western-style PCs got to the point where we could handle Japanese text characters properly, the domestic PC market kind of pitted out and just started using the regular IBM PC type technology because of economies of scale. But in mainframe, that was a very different story. Fujitsu had the market cornered and they defended it very well to the point where everyone who's still using mainframes in Japan pretty much is still using a Fujitsu mainframe. If you started with Fujitsu mainframes, you're still on Fujitsu mainframes. In fact, this is a business model Fujitsu's now embraced in other countries as they've gone around buying up what is essentially the national mainframe vendor that that governments used in each individual country. And this was a pretty smart business move, because if you're the mainframe vendor to a particular government, they have so much invested in terms of software and systems around your mainframe that they can't just replace it. They need something that at least emulates that mainframe. And of course the mainframe was incredibly proprietary technology, so they can't just buy something off the shelf. So they have to come back to the company that made it in the first place, who are now owned by Fujitsu. Which explains why in the UK, after they stuffed up the software contract with the post office and created a disastrous system that ended up with hundreds of sub-postmasters falsely being charged of fraud, they still got the contract to do the renewal of the computer system with the police service. But as ever, I've slipped ever so slightly off topic, so let's get back to the whole UltraSPARC and SPARC thing. As time went on, Fujitsu became Sun's closest partner on this stuff, with them working on the processes together, so all the later UltraSPARC designs, they're all done with Fujitsu and Sun working together. Now, a huge part of Fujitsu's interest in this is their mainframe market, but also, every single Sun machine that gets produced, there's a Fujitsu clone of this thing. Be it workstation or server, there's the Fujitsu version that looks almost exactly the same, only it's not got a Sun logo on it, and normally it has a slightly lighter shade of grey for the case. Sometimes they're even just completely white. In fact, once Sun's been gobbled up by Oracle, the last series of machines badged with Sun on, they've actually got processing that were entirely designed by Fujitsu, as Oracle had pretty much given up on the whole idea of designing a processor ever again. Now, earlier I mentioned UltraSPARC and said, we'll come back to that. Well, now's the moment that we come back to it. UltraSPARC is the next big leap in SPARC designs after the sort of original version. The first commercially released versions of the SPARC architecture, version 7, was the 32-bit design. We then got version 8, which really didn't change a lot, if I'm being honest, and stayed at 32-bit, and that's what the likes of the HyperSPARC's implementing. But when we get round to UltraSPARC, or version 9 of the architecture, that's when we make the shift from 32 bits to 64 bits. And this is a pretty big change, because not only do you have to become 64-bit, you also have to be fully backwards compatible with all the 32-bit code that's targeting the original SPARC designs, version 7 and 8 of the architecture. There's also some pretty clever changes around 9 as well that are not to do with going from 32-bit to 64-bit, but are there to help improve the performance of the processor in general. Now, they can do this because they've got a lot more code out there that they can study and look at what's being used on the processor and in what way. Right, let's get into the details of these changes between 8 and 9. And I apologise in advance, this is going to get very assembler and nerd orientated. But don't worry, I won't go into the excruciating detail of this. Version 9 of the architecture is defined by SPARC International, of which Sun were a member, so is Fujitsu and Amdahl, Cray, and Ross Technologies. I mean, a whole bunch of them. It wasn't just Sun, although Sun was a very significant voice within this body. And they had a not very easy task on their hands, in that not a lot of processor architectures had evolved from one bit width to another. So they didn't have an awful lot of examples to draw from. I mean, there's a few who had done this sort of thing before, but not necessarily overly well. And of course they had DEC chomping at their heels with the Alpha architecture, who had essentially just dumped VAX, created a new architecture that had ported their operating system across to it, and were using software emulation for the VAX applications. This was actually an approach they considered, and then dismissed largely because there's a lot of SPARC code out there, they still want to be able to run it, they feel like they're a relatively new processor design anyway. The other major example everyone's aware of is Intel's line of CPUs that started at the 8086. And by this point we'd well got into the 386 and 486 territory. So they'd recently done the transition from 8-bit to 16-bit to 32-bit. And the way Intel had handled this is, well, it's suboptimal. Now, originally they started off with a number of fixed registers for general purpose stuff, registers A, B, C, D, etc. So the way they'd done it is they'd made their registers bigger, as in they'd shifted them to 32 bits, and depending on how you named that register, depended on how many bits you got access to. So register B, for example, became EBX. And that got you access to the full 32-bit version. If you wanted a 16-bit version, well, you went a register called BX. So this meant CPU instructions would take these different register names. So say, for example, you wanted to add two 16-bit values together, well, you call the add op, and you'd supply it with the 16-bit version of the registers, and that way the CPU knew that it was going to add two 16-bit numbers together. Call it with the 32-bit register names, then it knows it's a 32-bit operation. Now, this is a very CISC approach to doing stuff, and burned through an awful lot of gates in the address decoding section. Now, SPARC came up with a far simpler and far more gate efficient way of doing this. They made all their registers 64-bit and had one simple rule. And that was that all existing instructions would generate exactly the same result in the lower 32 bits of this new 64-bit register. That meant that any 32-bit SPARC 8 binary could run on a SPARC 9 processor. So if, for example, we take the load instruction, the load instruction would load 32 bits from memory and deposit it in the lower 32 bits of the register, leaving the higher bits all as 0, I believe. The same with the store function, it would take the lower 32 bits in the register and write them into memory at the address specified. Now this of course meant that you needed new instructions to load 64 bits at once and save 64 bits at once, so they created two new instructions, load 64, store 64. There are a few other 64-bit instructions that needed to be created as well, things like multiply. But with this approach, you have to add surprisingly few 64-bit instructions, and you don't need a ton of address decoding logic and all of that stuff going on. Now these changes alone would have got us from 32-bit to 64-bit, and would have been, relatively performant. But as I said before, the difference between SPARC 9 and 8 was much greater than just shifting to 64 bits. With SPARC having been out there for a while, they've had a real good chance to look at real-world code and see where they're having performance penalties. And SPARC 9's where they chose to address most of those issues. And to be honest, they needed to. They weren't the only RISC processor in a Unix workstation out there by this time. In fact, pretty much everyone had their own RISC processor. HP had their precision architecture, SGI had MIPS, DEC had finally pulled its finger out and had created Alpha. IBM had got together with Motorola and taken their RS6000 system, and we got PowerPC out of that. So on every side, SPARC was feeling a lot more pressure. So let's have a look at some of the things they did. The first one I'm going to mention is that they added what's called a prefetch operation for the cache, so a compiler could explicitly tell the CPU to go cache some stuff that it knew it was about to cause the CPU to need. They also introduced a change where the CPU could now deal with misaligned data, i.e. a block of data that's not perfectly aligned on a 64-bit or 32-bit boundary. I think mostly this was to speed up Fortran stuff. One of the big things they introduced was the conditional move instruction. And the reason this is so helpful is because one of the most expensive things in terms of for the processor to do is conditional branching. This is because it will occasionally cause the CPU to actually empty the instruction pipeline, jump to a new set of instructions which may not be in the cache, and then start executing again. Where a conditional move gives you an instruction along the lines of, if A equals B, then set D to, say 7, else set to 8. Now in version 8, that would have been a bit of a problem. What you'd have is a compare instruction that checks to see if the two values are equal. You'd then use the branch not equals instruction. In the event that the two values you compared are not equal, well then it'd jump to label 1. In the event that they are equal, well then you'd stick the value of 7 into your register. We then have a little jump instruction to take us to the end of this block of code, and then we have label 1, which is the code we jump to in the event that they were not equal, and that's where we put the value of 8 into the register. The inefficient part of this is the branch not equals, as that's the bit where the code, branches. If we could get rid of this conditional, well, this whole thing would be a lot faster as the CPU wouldn't have a cache miss potentially. Now, using the move conditional instructions, we can do a much shorter version of that. I think that last one would be about 7 instructions at minimum. This one, we're going to do in 3 instructions, and also, we're not going to branch. So we can initially use the subtract and get a value out for that. Next, we can use an instruction called move if register 0. And we hand it the register we stored the value for the subtract in. If the answer is 0, i.e. the same, then we then move 7 into the register we want to store it in. If the value of the register we're testing is not 0, this instruction does nothing. We then have an instruction called move if register is not 0. And if the value of the register we stored our subtraction in is not 0, i.e. one of the numbers was different to the other, then this instruction triggers and moves the value of 8 into the register. So in this example on SPARC 8 we would have been forced to use at least 7 instructions and also had a conditional branch, and here on SPARC 9 we have only 3 instructions used and no conditional branching, and that is a lot faster to execute. Now it turns out a lot of their analysis of SPARC 8 code showed that most conditional branching that happens in a short memory range can almost all be replaced by these move instructions, so you can imagine the difference this made in terms of performance for a lot of code. There are a lot of other small changes they made in version 8 to 9 around this sort of optimization as well. Not so much this conditional move instructions, but there were lots of things that were there to help compilers along, like alias correction into their scheduling system, which is, to be honest, just a bit too dull to go into around here, but know that there's more stuff there than I'm telling you about right in this section of the video. In fact, from all these bits I've been talking about in Spark 9, I've been missing out some of the duller stuff that you're not going to be interested in, like, I don't know, error condition code registers and stuff like that. One of the big things I've not talked about yet is how they changed Spark in order to deal with operating systems a lot better. Now here they had a pretty great advantage. They could make more changes in this arena than they could in, say, the stuff that executed the user space code. And that's because Spark International was made up of basically everyone who wrote an operating system for Spark. So the people you needed to agree to this stuff were all sat round the table anyway and there to agree to it. Now, there's a lot of changes in this area. They completely changed how all the privileged registers work that only the operating system gets to make use of, introduced a new bunch of privileged instructions, but the big change they made, and the one that had the performance difference, and the one that I'm going to concentrate on, is how they changed trap levels. Traps were used by operating systems that ran on Spark to allow you to make the calls from user space back into kernel space. But on versions 7 and 8 of the Spark architecture, there was only one level of trap. And the problem with this is it meant that when you were in a trap, you couldn't possibly let another trap happen, or everything would go spectacularly wrong. So a large chunk of code for every single operating system call was all oriented around trying to make sure that other traps didn't happen. By introducing multiple levels of trap in Spark 9, if you're in a trap, well, another trap could occur, and you just have another level of trap. And then a trap could happen inside that one, and again, another level of trap. This saved the operating system having to do a whole bunch of stuff. So a call between user space and the kernel suddenly became a lot more efficient. We also gained a bunch of privileged registers as well, some global ones. Now this meant that when you made a call into the kernel, it didn't have to spend a big chunk of time storing all the registers into memory that were already there, so you could change them and then putting all the registers back when it was done. In fact, with lots of calls to the operating system, far more instruction time was spent dealing with pushing things in and out of registers and dealing with traps that almost all the CPU time inside that operating system call was going in this stuff. So Spark 9 really improved the efficiency of being able to deal with operating systems. Combine this with all the extra stuff they'd done to make user space code run faster, and the fact that we now have more memory bandwidth thanks to going 64-bit, Spark 9 is a heck of a lot faster than Sparks 8 and 7. Version 9 would also be the last version defined by Spark International, as by the time additions were needed to Spark 9, the only two people really left in the Spark space were Sun and Fujitsu, and they could just decide it between themselves. And most of these later editions were more around threading and again, stuff to do with multiprocessing, although Spark 9 really opened the door to very large multiprocessor systems. With Spark 9, some were starting to build machines with 1024 CPUs in there. Admittedly, not many people bought those machines because they used more electricity than a small housing estate. But if you were a large academic institution in need of a bit of supercomputing power, well, those Sun Starfire systems were, pretty good solution. Now, although this UltraSpark Spark 9 window becomes a bit of a boom in terms of number of Spark CPUs sold, it's a boom time for a limited number of companies making Spark chips. Sun and Fujitsu both do pretty well out of it. Ross Technologies, yeah, it doesn't end well for them. I believe TI just keeps chugging along with its embedded chips though, and does alright out of that. But this period corresponds with when the dot-com boom is getting going, and Sun are selling systems hand over fist. The rest of the Unix world is having a bit of a small implosion then, as Itanium's turning up and killing architectures left, right and centre. And despite its much vaunted performance statistics, and before anyone gets their hands on it, it turns out this thing is about as powerful as the average Vauxhall Nova. And then proceeds to go and basically die. I mean, Intel do keep this thing going because of a deal they've got with HP, and they're stuck making these things for nearly 20 years. But UltraSpark survives the vast culling of RISC architectures that happens around this period. But unfortunately for Sun, the dot-com boom turned into the dot-com bust, and the selling of expensive high-end systems based on rare CPU architectures starts to become, economically speaking, a little bit more dicey. But Sun chooses to do something with their Spark architecture that, well, it's actually really kinda cool. Sun helped start OpenSpark, an open sourcing of the Spark architecture, and they start by handing over the Verilog to one of their own CPUs. Now this is all released under GPL, so like the Linux kernel, anyone can take the source and modify it, just as long as they keep what they do open source as well. So that means someone could take this design, load it into an FPGA and have themselves their own Spark processor. Other manufacturers could take these designs, modify them and start putting them into ASICs if they wanted to. And Sun didn't just hand over this source code as a one and done, in sort of, there you go, people, get on with it. They followed up and made the next version of their CPU available. In fact, this keeps going right up until the point where they're purchased by Oracle, and then, yeah, they don't contribute to anything anymore. So what happened to the Spark architecture? Well, the simple answer is it's not dead yet. Sun, who had been one of the leading contributors to the whole Spark design ecosystem, did keep going helping to design UltraSpark even after they got taken over by Oracle, although for a brief while. Oracle then took the decision to shut down the Spark Group by dint of letting almost everyone who worked for it go, and then formally announcing that they were closing it after that. Although Oracle kept making UltraSpark based servers, and that was largely using either older designs where they'd up the clock speed on them, or using designs from Fujitsu. And this has left Fujitsu as the last player standing in the world of Spark. In fact, last year they announced that they were going to design their final iteration of the Spark architecture, which they were going to use in their mainframe platform. And again, that next version of the mainframe platform, that is going to be the last version of that mainframe platform. Their intention is to move customers onto that who need continuity of service, and whilst they're on that version of the platform, migrate them off to more emulator-based solutions. Although I should mention, a mainframe has a really long support tail, so even after they stop producing that mainframe, there will still be support for it for a very long time to come. But you do need those sort of timeframes when you're migrating stuff off a mainframe platform. When you hear about these major IT failings that mess up, say, banks being able to take card payments, or British Airways being able to do with luggage or book flights, that's usually a rushed and bungled migration off a mainframe platform, followed very quickly by a migration the heck back. There is also still plenty of business being done in the embedded end of the Spark market. Plenty of chips have an IP block from Spark just embedded on in there, doing their thing, and will do for a very long time to come. The open sourcing of that stuff pretty much guarantees it's going to be there for a long time. Well, if you've made it all the way to the end, I'd like to say thank you very much for watching. It does feel like this has been a particularly long video about a CPU architecture, but with most CPU architectures, there's one company behind it. In this case, there were dozens. I hope you enjoyed watching the video, and if you did, YouTube has handily provided the button to indicate that fact, known as the thumbs up. Ooh. And if you'd really like to help the channel out, why not hit that subscribe button and gently tickle the bell, as that encourages the YouTube algorithm to inform people that we've actually produced a video.